Hello, my name is Cristina Anita Rotaru, and I'm a professor in the Corey College of Computer Science at Northeastern University. I'm here to talk about our work on automatically finding attacks against BBR, and this is work conducted by my former students, Anthony Peterson, Samuel Jarrow, and Endandul Hogg, who all graduated, and with my colleague Dave Shopness from Northeastern University. So one of the problems that we have been interested in working on in my group for quite some time is looking at how do we gain assurance about protocol implementations. Assurance about the fact that they achieve their properties and that they are not vulnerable to attacks. And there are different directions that somebody can pursue when examining these kind of problems, from looking at correctness of the algorithms, for example, security properties, proving security properties, or looking at how to show that the protocol provides its functionality by applying model checking. And last but not least, by just simply testing implementations of these protocols, but in a smarter way, not just randomly throwing inputs at the protocol. And this is a challenging problem on many levels. First, when we look at requirements, there is a very uneven culture of specifying these protocols. And often there are a lot of details missing about what they are supposed to achieve. And also some goals are really difficult to formalize. When we're looking at designs, often models do not capture optimizations and design decisions that are made at the implementation time. And last but not least, when we're looking at implementations themselves, sometimes it's very difficult to find all test cases, to have good coverage for them, and also to reproduce conditions that are very similar to deployment conditions. And this is something that we've been spending quite some time in my group looking at from protocols like QUIC, TLS, TCP. We look at secure routing. We also look at how to check compliance for some of these protocols. And probably the most relevant to this particular work that I'm presenting today is this direction of adversarial testing, in which we created a number of frameworks that test distributed systems and network protocols in a smarter way. Our most recent work in this space is TCP, and in particular, we look both at the connection establishment and congestion control. So this brings me to the topic of today's talk, congestion control, and why it is important. The main goal of congestion control is really to avoid overwhelming the network. And it was created, in fact, because such a congestion collapse happened in the internet some time ago. And the way protocols react or try to handle these kind of situations by looking for signals from the network itself about such a congestion happening. For example, TCP congestion control leverages acknowledgements for data packet sent to detect packet loss. And there is an implication that this packet loss really means that there is congestion in the network. These acknowledgements, unfortunately, are sent in the clear. And there is very little protection, with the exception of the random sequence number that really an attacker will need to guess in order to be able to inject in the stream. There is really no other protection for these acknowledgement packets. Thus, an attacker that is able to bypass this check of the sequence number, either by being on path, where he really can observe the sequence, or by being off path and predicting what that sequence is, he will be able to create problems for the congestion control mechanism. And as a result, we can have the sender sending faster or sending slower, or just have stalled connections. Why do we care? Well, the main reason that we care is because we rely on congestion control in the algorithms, in the protocols that we're using, TCP or QUIC, to keep the internet stable. And if attackers are able to create these kind of attacks, not only that they can impact particular target victims, but they really can almost cause also congestion collapse. In our previous work, we studied loss-based congestion control. The reason is because most of the algorithms supported by TCP, from TCP, Neutrino to Cubic, use this kind of congestion control algorithms. However, there is a new algorithm called BBR that follows a different approach. It is not using acknowledgements as an indication for packet loss. So the question that we're asking in this work are, is it the case that even if BBR is using a different congestion control approach, is it still vulnerable to this kind of acknowledgement manipulation attacks? And also another question that we are asking, are there any known attacks that BBR is immune to? And in the next of the talk, I'm going to tell you a little bit about this. First, I am going to give you some background on BBR. Then I'm going to discuss our methodology to find attacks and present some results. So first, let's start with a high-level overview of BBR and its motivation. Protocols that use packet loss as congestion signal, the reason that they do that is because they really look at it as an indication that there is some queue that is overflowing along the path due to congestion. However, what happens in modern networks is that because modern switches have large buffers, by the time the congestion or the packet loss is detected, right, because of these acknowledgements, it really becoming detached from congestion itself. And really what happens is that we end up with situations where the network is not used efficiently. And we have these large latencies that accumulate in the network. Stepping back and really looking at what's going on, one can also notice that, in fact, what really a protocol would like to find out, it's not if there is packet loss or not, but what is the bandwidth of the bottleneck link. And the reason is because the protocol should not send faster than that, right? We need to send at that pace, and then you can use information about RTT to basically know how much data should you have in transit. And this is exactly what BBR does. So BBR, its main goal is to estimate the bottleneck bandwidth. And of course, it's doing this still by using some form of acknowledgements across several RTT intervals. And then as a result of that is then trying to stay as close as possible in terms of sending rate to this estimated bottleneck bandwidth, as shown in the graph on the right, where with blue we see what BBR is sending, and with the green we see what BBR is sending, and with blue we see the bottleneck bandwidth. As a reminder, again, attacks we're looking for are these acknowledgement or ACK manipulation attacks. And to get even a little bit more into the details of this, the acknowledgement actually carry a lot of information about the protocol. So the attacker can really influence what it wants to create in terms of the effect by exploiting the semantic or the meaning of this acknowledgement packet, and particularly the number of bytes that are acknowledged. And we want to find such attacks in an automatic way. So the way we do this is by leveraging our previous work. It's called tcpone. And this is a fuzzer that we created in order to automatically find attacks against TCP congestion control. It really assumes that the state machine that is used is based, or it shares similarity with TCP and Neutrino. However, what tcpone had that was really very instrumental in finding these attacks automatically and very effectively was that used the state machine of the congestion control algorithm to find all possible situations that will lead to increase, decrease, or stalling of connections, and find a list of what we called abstract attack strategies. Why abstract? Because we just know what is the effect, but in practice, that can be achieved by manipulating this acknowledgement packet. So then what tcpone did is map these abstract attack strategies to concrete attack strategies, and then inject this at runtime. And these concrete attack strategies means actions with respect to acknowledgement packets conducted in a particular state of the state machine. So the algorithm needs to, the tcpone needs to know what is the state of the congestion control algorithm at the runtime. So what kind of actions are we talking about? I'm talking here about on paths. There are also some off paths that we didn't find to be very effective. Things like duplicating acknowledgements, or sending a burst of acknowledgements, or acknowledgements things that you have not received, or acknowledging the same packet, or stretching a particular number of bytes that needed to be acknowledged over several acknowledgements. So these are all actions that are supported already by tcpone. However, what tcpone did not have, tcpone did not have the BBR state machine. And in fact, this is one of the moments where we really discovered that there isn't such state machine anywhere other than the code. And so we examined the code, we looked at documentation, we looked at presentations in order to come up with a BBR state machine. And I'm showing it here, just kind of to give you an idea that it's quite complex. It's not like 3 states and a few transitions. And so we extracted this state machine, and we use it to find these abstract attack strategies, and then we modify tcpone to infer the state machine and to detect the state at runtime, because that's when the attacks need to be injected. And so by doing this, we ended up with quite a number of attack strategies. The way we do this work, we then classify them based on what the effect is, and also based on what is the particular action that led to that effect. Each action has lots of parameters. And so when we say a class of attacks, we mean that that is the operation, but that operation was performed with several parameters and in different states of the state machine, of the algorithm, with the same effect. So we did find attacks that made BBR to send faster, some that made BBR to send slower, and some that made BBR stall the connection. And the stalled connections are particularly interesting because basically what happens, you end up with connections where you don't understand why your file is not progressing because everything else seems fine, right? So there is actually traffic going back and forth. It's just like no new data is sent. So let's look at a few attacks that we found. One of them is optimistic acknowledgement. It was an attack that, it's an attack that made BBR send faster through an optimistic acknowledgement action, where the attacker basically what was doing was acknowledging the highest observed data sequence. And as we can see on the diagram on the right, BBR, every time thought that everything was received, will follow the protocol and send 25% faster. And we see that the aggregate follows the increased sending rate. Another attack that we found was conducted through delaying acknowledgements. So in this case, was an attack that made the BBR to send slower. There were many variants of this attack in which the attacker will delay the acknowledgement for a constant amount of time. Another attack that we found that also resulted in sending slower is where BBR is made to believe that the congestion is bad. So basically, there are several times on which the RTO occurs. And the sender basically sends very little data in between these RTOs. And this kind of behavior, we were able to create it with either limiting acknowledgement or stretching acknowledgement. And again, as a reminder, a limited acknowledgement was the action where the attacker keeps resending or acknowledging the same data, while stretching is where it's really, instead of sending one acknowledgement for the entire number of bytes that are acknowledged, he will send a few of them. So that slows it down. There were also a number of attacks that we found that were not effective against BBR. So these are attacks that we found in the past automatically against TCP congestion control algorithms, and they were also conducted through acknowledgements. So in particular, they are sending bursts of acknowledgements or sending divided acknowledgements, right? So where again, the attacker will take some number of bytes and automatically divide them equally over several other number of acknowledgements, or sending the same acknowledgement multiple times. And in all these cases, for different reasons, they didn't work against BBR. For example, right, the last one, the duplicate, is quite obvious because duplicating the acknowledgements in loss-based congestion control algorithm, it has a meaning, it's an indication in the algorithm that detection of that loss occurred, right? BBR doesn't even have this kind of behavior. So to summarize, we examined BBR congestion control algorithm, and even if it's using a new mechanism in which instead of using acknowledgements to detect packet loss, it uses acknowledgements to estimate the bottleneck bandwidth, and also then use that information in a more sophisticated way to adjust the send rate and the data that is kept in traffic in the network. We found that BBR is vulnerable to acknowledgement-based attacks. We found one type of attack where BBR could be made to send faster. The others were either sending slower or stalling. And we also found a number of attacks that were not effective. The code is available from Samuel Gero's GitHub in case you want to check it out. And also we have a number of our papers on the project website, work looking at the big picture that I was mentioning at the beginning of the talk. You know, how do you prove protocols properties in terms of cryptographic properties? How do you look at security properties when you have protocols stacked on top of each other? Maybe last comment that I can also make is that BBR, we look at the BBR implementation in TCP. BBR will have it will be much more difficult to attack BBR in QUIC for the main reason that QUIC, it's implemented on top of UDP and it's using encryption. So the headers are going to be encrypted. It's something that we're looking at and we'll hope to have some results soon. Thank you.